Hey, take a quick look around you. Really look at the food you ate, the clothes you're wearing, even the device you're watching this on right now. What's the one thing they all have in common? Well, the answer is almost always carbon. It is the absolute fundamental building block of life and pretty much everything we've built. But it holds a really fascinating secret. And this is where things get kinda weird. For an element that is so important, so central to everything, it's actually incredibly rare. So that brings us to the big puzzle we're going to solve in this explainer. How can something so scarce be so absolutely essential to all life? It's hard to wrap your head around just how little carbon there is to go around. In the entire crust of the Earth, it's a tiny 0.02%. In the whole atmosphere, just 0.03%, mostly as carbon dioxide. So how on earth does this incredibly rare element become the literal backbone of every living thing we know? Well, this is what we call the carbon paradox, and the secret to its massive importance isn't about how much of it there is, but about what it can do. It all comes down to its unique chemical properties that make it totally unlike any other element. To really get carbon's secret, we need a quick look at how atoms connect with each other. Now, most atoms form what are called ionic bonds. Think of it like a simple transaction. One atom gives an electron away, another one takes it. Simple. But carbon does things differently. It prefers covalent bonds. And these aren't a transaction, they're a partnership. Atoms share electrons. And that single idea, sharing, is the key to everything. But here's the thing. For carbon, making these sharing-based covalent bonds, it isn't just a preference, it's pretty much the only way it can become stable. Let's just put ourselves in carbon's shoes for a sec. It has 4 electrons in its outer shell, but it really wants a full set of 8 to be stable and happy. So, option 1, gain 4 more. Problem is, its tiny nucleus only has 6 protons. It's just not strong enough to hold on to 10 electrons. The whole atom would fly apart. Okay, so option 2. How about just getting rid of those 4 outer electrons? Well, that would take a huge amount of energy. It's just not practical. So, if you can't gain them and you can't lose them, what's left? You've got to share. And that right there is a covalent bond. It's that partnership where atoms share their electrons to make everyone stable. It's a strong, cooperative connection, and it is the absolute foundation of carbon's incredible power as a builder. So this whole force-to-share strategy ends up giving carbon 2 distinct chemical superpowers, and it's these 2 properties that let it act like the universe's ultimate Lego block, building all sorts of amazing, complex things out of just a few simple pieces. Okay, superpower number 1, tetravalency. It sounds complicated, but tetra just means 4. Because carbon has those 4 outer electrons to share, it can form 4 strong bonds. At the same time, this means it can link up with a huge variety of other elements, hydrogen, oxygen, nitrogen, you name it, and build these complex 3-dimensional structures. But its second superpower, catenation, is even more amazing. This is carbon's unique gift for forming strong, stable bonds with itself. It can link up, carbon to carbon to carbon, forming these incredibly long chains and complicated rings. It's like atoms holding hands with each other, creating a backbone for millions of different molecules. Seriously, no other element does this anywhere near as well. And this power of catenation leads to some wild results. Just by changing how carbon atoms bond to each other, you can get completely different materials. In a diamond, for example, every single carbon atom bonds to 4 others in this super rigid 3D structure. That's what makes it the hardest natural substance known. But in graphite, each carbon only bonds to 3 others, forming these flat, slippery sheets. That's literally why the lead in your pencil works. It's the same element, just arranged differently. Okay, so with these 2 superpowers, bonding with 4 other atoms and bonding with itself, carbon basically opens the door to an almost infinite world of different compounds. So let's zoom in on one of the most fundamental groups, the hydrocarbons. Just like the name says, hydrocarbons are just compounds of hydrogen and carbon. They're usually grouped into families based on how they bond. You have alkanes, which only use single bonds. That means they're holding as many hydrogen atoms as possible. We say they're saturated with hydrogen. This makes them really stable, not very reactive. But when you get double or triple bonds, like in alkenes and alkynes, they have fewer hydrogen atoms, so they're unsaturated, and that makes them way more reactive. And believe it or not, this little distinction shows up everywhere in our daily lives.
Yeah, because these ideas aren't just for a chemistry textbook. They're at work all around us every single day. Let's just take one super practical example you probably use today: soap.
A single molecule of soap is an absolute masterpiece of carbon chemistry. It basically has a split personality. One end is the hydrophilic head, hydrophilic, water loving. The other end is this long carbon chain called the hydrophobic tail, hydrophobic, water fearing. It hates water, but it's really attracted to stuff like oil and grease. So check out how this works. When you wash your hands, all those little water-hating tails dive into a particle of grease, completely surrounding it. The water-loving heads stay on the outside, facing the water. This creates a tiny little sphere called a micelle, which has the grease trapped safely on the inside. Then, when you rinse, the water just grabs onto all those heads on the outside and washes the entire grease-filled package right down the drain. Pretty clever, right? And hey, that whole idea of saturated versus unsaturated carbon chains, it's also super important for our health. Animal fats, for instance, tend to be packed with long saturated carbon chains. That's the less reactive, more stable kind. But healthier vegetable oils, they're full of unsaturated chains, the ones with the double bonds. It's this tiny difference in carbon bonding that explains why we're always told to cook with oils that are rich in unsaturated fatty acids. So, when you add it all up, its ability to form four bonds, its power to create endless chains, and all the different types of bonds it can make, you get this. There are over 2 million known organic compounds based on carbon, and we're discovering more every single day. From the simplest fuels we burn to the most complex molecules of life itself, it's all built on the incredible versatility of this one element. Its amazing flexibility is exactly why carbon is the foundation for every single living thing we've ever found. But that leaves us with one final and really cool question. Is carbon the only way? Could life on another world with totally different conditions be built using a completely different elemental backbone? Maybe something like silicon, its closest chemical cousin. It's a question scientists are working on right now, and it's definitely something to think about. Thanks so much for joining me.